And welcome, everyone. Thank you so much for joining us here for the Battery Insider podcast. And we're today in Detroit for the North America Battery Show in the United States. And it's a really busy day. A lot of things are happening. And I'm extremely delighted to have Li Shi with us, who's the Chief Executive Officer of AM Battery. So wonderful to have you.
Thank you. Nice meeting you, Simon.
Perfect. So I think, today we want to talk a bit about dry electrode manufacturing. I think it's one of these topics actually a lot of you have been requesting to hear more about. So I'm really excited to have this conversation. And yeah, maybe just to kind of start a bit, if you could start by introducing your company, give us a bit of an overview of AM Battery.
Okay, maybe I can start with the history. The company was founded in 2016 by two professors. One of them is from Texas A&M. The other one is from Worcester Polytech Institute. And they want to solve one problem, which is how do we get rid of the solvent used in making electrode? And the traditional way, we call it a wet process, is mixing active materials with conductive material binders, but using a solvent. And this solvent happened to be a lovely chemical, toxic material called NMP. And so two professors thought, if we can use a dry process without using solvent, it can save a lot of energy and save a lot of space, and also without using toxic materials. So then they founded the company, and then for the next 4 years, they were working in the lab and writing papers and start to progress. But then Battery Day happened. This is precisely 4 years ago in 2020. And Elon Musk get on the stage and said he's going to make the 4680 cells and from the skinny 2760. And also he said he's going to reduce manufacturing costs by 40% by turning the dry process into a real manufacturing process. And so that is a game-changing moment for the industry and also for AM batteries, because the founders realized the moment for AM battery has arrived. So within 12 months, they raised the seed round, and Series A followed within 12 months. Then last year, October 2023, we raised $30 million, this time led by Toyota Ventures and other major investors. So we felt we finally arrived, and we moved into a new facility, start to develop engineering pilot lines. Our business model is to sell turnkey equipment for battery makers to make electrode using the dry process.
That's awesome. Maybe also just one quick word about yourself, right? Because I think you have quite a different experience as well.
Interesting, yeah. And I have been in the industry for over 20 years. And before I joined AM Battery, maybe 14 months ago, I was running Celgard. I was the president of Celgard for a few years. And Celgard was a company, maybe the largest separator producer in the US. And when the board of AM Batteries called me up, and I was intrigued. And once I looked into this technology and realized this could be an opportunity to change the landscape of manufacturing. So I just felt privileged to join the company. And in your lifetime, you don't have many chances to say, I can compete against Tesla and become the major player in the new space of dry battery electrode.
That's so fascinating. I think it gives you definitely also the credibility to run things at a big scale. I think as you've done with Celgard. And then maybe a little anecdote to our listeners, actually have something in common, because also we as Battery Associates had our first Battery Associates Battery Day one day after the Tesla Battery Day. That's also 4 years ago.
Interesting.
Started. So you might have a similar type.
Yeah, it is a big game-changing for you as well.
For us as well, because there's a lot of inspiration we took from that as well, which was amazing. Maybe now for the listeners, right, who don't know so much about, how your process, you just mentioned this turnkey solution you're developing, how does this differ to the current?
Very good. Yeah, maybe I was too quick earlier. But the current wet process is, you can say it's a relatively simple process, but they use a solvent, there's an NMP. They mix material together to make a slurry. Slurry is just a layman's maybe expert expression, liquid mixed with powders. Then you start to coat them onto metal foil. And the metal foil, we usually call them current collectors. Then after coating, you have to send them through this huge oven to dry off this lovely chemical called NMP. And the NMP not only toxic, it is has a very high boiling point of 200 centigrade. So considering how difficult to dry off water, this one is exponentially more difficult to dry off. That's why for anyone building a gigafactory, they usually have a 100-meter long oven to just dry this material off. Then they have a recovery system to keep them inside because the material is toxic. Then some advanced companies process them again and use them again. But early starting companies, usually they sell them to the chemical companies. So as a result, overall NMP material is also very expensive. And talking to any battery makers, they will tell you more than 40% of energy is consumed by this drying oven. And that's why if you can get rid of this, that can really save a lot of energy. So the operating expense, carbon footprint, and also capital expenditure will be reduced dramatically. We usually use this 40% reduction as a member. We file against the wet process. Dry process will save energy by 40%. And we can reduce, with our unique technology, can reduce space usage by 70%. So that's a big saving for any battery makers. Especially nowadays, the low-hanging fruits are being taken. And any technology can come in, can have this kind of dramatic reduction. It's make it very attractive.
I think especially at the topics of cost and also sustainability are really big ones. I think these ones. I see this also in Europe, PowerCo and other companies talking about that as well. Maybe you just, because you mentioned now there's 40% cost reduction, right? And I guess, is this now on the OpEx side, CapEx, or if you could maybe share a bit more on the OpEx, CapEx talk? Is there something more?
So on the capital expenditure and also operating expenditure perspective, we felt it can reduce cost by 40% across the board. Yeah, for both of them. And when you get to the whole battery production, and we think if you have $100 per kilowatt hour cell, and by using dry process, you can reduce the cost by 10 to 15%. So that's a huge number, $10 to $15.
One of the steps, yeah. Maybe to understand a bit about compatibility with different chemistries and technology. So, is it like chemistry agnostic, the process? And also can you use it with all kinds of different battery chemistries, or are there some where it's more difficult?
So we have tried in the lab a few things, and definitely it works with the NMC, whether it's low nickel 622 or 811. And also we're trying with LFP, that is working. And also we're working with silicon anode, which is working as well. And sodium-ion, we'll also try some material that is working. So it's maybe I can call it agnostic chemistry. One thing we cannot do is lithium metal anode, because our unique process is electrostatic deposition. Yeah, we are using electrostatic deposition to put this powder onto metal foil. So if the material is conductive, then it doesn't work in the electrostatic approach.
And then also kind of, thinking about this, right? Like, so what's maybe some of the limitations? You already mentioned with the metal there. But other ones, like, rumors are about other companies trying to make this work as well. That scale up is really difficult as well. Like, they can do it in a smaller scale, but to get it at a high, volume, consistent scale is very difficult. Maybe if you could share a bit more about that.
Okay. So good question, because at the chemistry and the physics level, at a first principle perspective, I think that this is agnostic. But we're facing the same challenge everyone is facing to scale up the engineering piece. So that is the challenge we're facing, because on three fronts, we need to make the film wider, and we need to make the film very uniform, and also we need to make the speed up so it can compete with the wet process. And actually just on Monday, we made an announcement that we ship some rolls of film to our one of our customers, and made with the engineering pilot line. This is the first time we send rolls of film. Until this point, we usually send the sheet samples. And now the battery makers can make a large battery pouch cell and they can see how it stack up against wet process technology. Yeah, that's a major milestone for us.
Congrats! No, that's big. And I think then also the volume and the consistency, these kind of things are really crucial, right, for getting the right adoption. Yeah, so maybe you can also talk a bit about, energy density topics. Is there any differences? What hour per kilogram we kind of can get to, or is it all in the calendaring, or just kind of understanding, or like, are there any differences?
Okay. So on the energy storage or energy density perspective, it's driven by the original chemistry, right? What cathode, anode you are using. But overall, we can increase energy density by 5 to 10% because we can load up the thickness more easily than wet process. Wet process, if you start to get the cathode material very thick, uniformity is an issue, and also the drying become even more expensive. So people usually do not make very thick batteries. And with our process, our deposition can get it loaded up very high. And actually, we try to loading maybe 5 times of the wet process. We don't need to go that far, but just by doubling the thickness, we can increase the end result of energy density by 5 to 10%.
Can you share a bit like what kind of thickness can you get to?
Yeah, we can get to 120, 130 microns. The usually is 60 micron right now.
I mean, sometimes higher, depending.
Yeah.
Then I guess also on the energy density, because it's a bit different with which kind of binders you're also using, right?
Yes.
And do you need more binder than a liquid process?
No, we are trying to make it similar. So this is where we're trying to make the lighthouse customers, which is a word I recently learned means early technology adapters. I want to make them feel comfortable. So the barrier to entry for them to accept this technology became lower. So I just usually tell them what binder percentage you like and what cathode material you like to use. We'll try to have the same percentage of active materials. So as a result, usually they try it, then they can have a comparison very quickly, then realize, oh, this one actually works.
Because I think that's really important, right?
Yeah, very important.
You want to be able to kind of essentially just do what they already have done.
Yeah.
Like at least a composition and do it in different processes.
Yeah, they have one less thing to worry about, because with 4M change in the battery makers, you don't want them to change the materials. You just change the machine. So that's why after they make the comparison, they say, wow, this rate capability, energy density, and the cycle life are all equivalent. And of course, we do have a more ambitious plan trying to make the dry process even better than wet process. This including increased thickness. And also we signed a joint development agreement with Xeon, which is a major binder player. We ask them, let's develop a binder for the dry process. Because nowadays, most of binder is tailored. They have put a strange additive in to make a wet process work. But I said, take those out. I don't need those. Just develop a clean binder for us. So that's very exciting. That's our next generation product.
Because I think, as you just said, right? Because that's one topic also I've heard is that there's been some discussion, I think more PTFE based and different binders which are used for a lot of the dry processes. And some people are looking for more like, other alternatives for binders, right? Like more sustainable ones, removing fluorines and things like this. And I think there's a lot of potential development as well.
Yeah.
Also in that.
And also I want to use the opportunity to clarify one thing.
Please.
I mentioned Tesla, right? And I want to say we are different from Tesla from 2 perspectives. One is the technology is different. And I think most people know the history of Tesla's dry process. They bought a company called Maxwell in 2019. And then 2 years later, they actually sold the Maxwell supercapacitor business back out into the market. Then they kept the dry process. That process is using PTFE that you mentioned. It is a very difficult material to work with. That's why the mixing part is so energy intensive. And also PTFE is not stable in anode if you use it in the anode production. That's why our approach actually do not use PTFE. So this is a key differentiation I want to emphasize. And the second part is even though Tesla's technology is competitive against A and Bs, but we are not working in the same space. You know, they are battery makers, they make cars, and we are equipment producer. Down the road, Tesla could be our customers. So that's a clarification I want to make.
I think it's an important one. So like just last thing on the binder. So what kind of binder? Do you use like more PVDF ones?
Yeah.
Like just standard ones?
Yeah, that's why, just like I mentioned earlier, you use a PDFE and give it to me, and we'll grind it in the right particle size. So we just need to control the particle size and the flowability and how it handles in the electrostatic deposition. So,
and maybe just as a kind of like a last question, because this sounds great, right? I think everyone wants that, right? We want to have low energy requirements, lower costs. You know, I think that's everyone is looking for that. But from a timing perspective, you know, when do you think this will be, like, you know, what do you think when this could be common in the market or more widely adopted?
Okay.
Yeah, maybe whichever.
So I was talking with Kurt Kelty at the GM this morning, and also talking to some expert in the marketplace. We felt that in 5 years, it will reach a percolation point. Then the major players will all adopt this. Then in 10 years, it will be prevalent in the all gigafactories will be using this technology. And for AM batteries, we are finalizing the engineering pilot line. So we start to have a selected customers we want to sell this engineering pilot line to, then allow them to get into this field very quickly. And also talking with the major players in the world, very quickly we found out everyone is working on the dry battery electrode process. Then when they look at our process, they usually have 3 reactions. And one of them is, okay, let's have a JDA start to get into the qualification of your program. So that is one group. Then the second group is we are working with the Tesla equipment provider, because some people who sell the equipment to Tesla, now they start to promote themselves as an equipment maker for dry battery electrode space. So we want to try that approach because Tesla has proven it works. We think we can catch up. Then the third group is some Japanese companies and the Korean as well. They said we have our own approach and we want to try it ourselves. So those are the 3 reactions, which is very reasonable. I think we understand we are a relatively young company. And so for us, first thing is we need to catch up with Tesla in terms of commercial capabilities. Then we want to leapfrog them. And we're very happy, actually, we recruited the engineering director who used to work at Maxwell, who invented the dry battery electrode process. And last year, he joined AM Batteries and from Tesla. And so we're very happy because when people ask him, why did you jump ship? He said, wow, we found out the AM battery may have a better mousetrap.
That's exciting. I think one last thing on this one, do you think, because a lot of people, for example, for solid state, right, I get asked like, will this replace all the other, you know, the existing technology we have? Same with this, like, is there any reason why, in case it all works out as you dream, right, like as you're working hard on, is there any reason that wet process would still exist, or like are there some reasons, or would it be that there's no reason that dry could in theory replace all of the wet process?
Interesting. I think high precision, maybe consumer electronics, that require, I think the wet process people are continue to advance their uniformities. And I know that consumer electronics like iPhone, Galaxy, those still require extreme precisions. And we know, and also from the safety reasons, uniformity sometimes affects safety. Do you remember Galaxy Note 7, right? And that's just because they went very thin with a separator, like a 5 micron or 7 micron, and the uniformity wasn't very good, and the safety feature was not well covered. Then it started to hurt the battery. I felt maybe very high end, you will still have a wet process, high precision manufacturing are required.
So there's like some But then for like automotive and BESS and things, you think that
Yeah, I think the maybe automotive energy storage system should all go to dry very quickly.
because they're also very cost sensitive, right? And I think
Yes, very cost sensitive.
from our automotive customers, it's all about reducing costs.
Excellent. You capture a very good point. Cost sensitivity is very important. Yeah.
Brilliant. No, Lee, I really, really appreciate these insights.
Thank you.
I'm very happy both of our companies are similar age, so let's keep growing. But no, really appreciate these insights and look forward to staying in touch.
Yeah.
And also want to thank all of you listening to the Battery Insiders podcast today. Again, here as a US version at the Battery Show in North America. Big thanks also to Informal Markets for having us here. And again, hopefully you subscribe to our YouTube channel or Spotify or anywhere else you listen to this podcast. And hopefully talk and see you very soon. Thank you all.
Thank you, Sam.